I'm Sean Daly, Associate Vice President for Alumni and Parent Engagement and Annual Giving, the parent of 2 Kenyon students and one of the Bicentennial Tri-Chairs. It's my pleasure to welcome you to the second installment of our Bicentennial Faculty Lecture Series. This 6-part series will highlight some of the college's best-known faculty members and cover a variety of topics in the fine arts, humanities, natural sciences, and social sciences. We're joined tonight by Associate Professor of Physics Madeline Wade. Wade joined the Kenyon faculty in 2015 after earning her PhD in physics at the University of Wisconsin-Milwaukee. She is a member of the LIGO Scientific Collaboration and works as a data analyst on the experiment. Most recently, her research time has been focused on calibration of the LIGO detectors and using machine learning algorithms to improve the quality of LIGO data. I'll turn it over to Professor Wade.
Thank you for that introduction, Sean. I will share my slides here. Okay, so thank you everybody for coming. I'm hoping to take the next hour to teach you a few things. I hope everyone gets to learn something new today. We're going to explore the densest objects in the universe. So I'm going to have to teach you something about gravity. I'm going to hopefully teach you something about compact objects and teach you a little bit about machine learning and the techniques that we're using in my research group at Kenyon to help us learn about these dense objects. I also have to give a shout out because I saw him enter the room, but I've listed all my collaborators, which includes a large number of current and former Kenyon students on the title slide here who have all worked on these projects, and at least one of them is here tonight. So very excited to see that. So our story is going to have to start with the life cycle of a star. Maybe you know a little bit about the life cycle of a star, but if not, a star is born from a cloud of gas and dust that we call a star-forming nebula. Something has to trigger a collapse in this cloud, but once that's triggered, then parts of the cloud will start to collapse on itself, get denser and denser, and get hotter and hotter, and eventually get hot enough to start undergoing what's known as nuclear fusion, which is what powers stars. That's what will start the part of a life called a protostar, which will eventually evolve into a star, for example, like our sun, if it has a mass that's around the mass of our sun, or if it's much more massive, like something that's maybe 8 or 10 times as the mass of our sun, it will follow a slightly different life cycle. The star will burn through its fuel, burning hydrogen and helium and heavier elements through nuclear fusion. But eventually, all stars will get to the point that they run out of gas. They run out of things to burn, and so they no longer have a way to support the inward collapse of gravity. Gravity is trying to pull the star together, and the nuclear fusion is helping to push it apart. The eventual end of the nuclear fusion fuel leads to one of 2 possible end lives for a star. If you have a star like our sun, it has this sort of beautiful floating away of the star's outer layers in something known as a planetary nebula. And the dense core of the star is left behind in a remnant known as a white dwarf. So this is one type of compact object, and this is the fate of our sun. It will one day become a white dwarf. However, if you have a more massive star, something, maybe 8 or 10 times the mass of the sun, the end of that star's life is much more dramatic. The outer layers collapse on a dense core and rebound in what's known as a supernova explosion, which is a very energetic and dramatic astrophysical event. And what's left behind as those outer layers rebound is the very dense core of this massive star. And there are 2 options for what that dense core can become. Both are equally exotic and exciting. The maybe slightly less dense, the slightly less dense option is something known as a neutron star, which is basically a super dense ball of neutrons. Neutrons are electrically neutral subatomic particles. The other option is the densest you can possibly get, which would be something called a black hole. And I should mention that these explosions, this end life of either the massive star in a supernova or the planetary nebula, this is the type of thing that triggers new star formation. So this is what we call the life cycle of a star. The death of some stars will trigger the collapse in these star-forming nebula to trigger the birth of new stars. So that's a little bit about the life of a star. We're going to focus in on these dense objects, starting with the slightly less dense objects of neutron stars. Neutron stars are pretty exotic and exciting astrophysical bodies. They have incredibly strong magnetic fields. So you've probably heard of the Earth's magnetic field. We like it. It does things like protect us from bombardment from cosmic rays and things like this. The magnetic field of a neutron star is actually trillions of times stronger than that of the Earth's. Neutron stars are also incredibly rapidly spinning. When you take a star that's spinning a little bit, like our sun we know is rotating, and you collapse it down to a tiny, compact core, it turns out conservation of angular momentum is going to speed that thing up. And so it's going to be even more rapidly spinning than the starting star. These things spin a full rotation in could be as small as just a fraction of a second, like milliseconds, to as much as maybe a few seconds. So faster than a kitchen blender in the fastest situations. And they're incredibly dense. 1 teaspoon of neutron star matter weighs 10 million tons. This is not a density that we will ever see or produce on Earth, at least not anytime in the near future. And additionally, they can emit light from their poles. So you can have this emission of these jets of light coming out of the poles of the neutron star. And as it's spinning by you, you get this lighthouse effect where the radiation being emitted by the poles of this neutron star will hit the Earth if it's beamed at you in these cyclic pulses. The type of neutron star that is emitting this light out of their poles and spinning rapidly, these neutron stars are known as pulsars. Or said more simply, neutron stars that behave like lighthouses. Those are the ones we call pulsars. Pulsars, the emission from the jets that can sweep past you if it's beamed at you, is most strongly emitted in radio wavelengths. So you all are familiar with light because you all have eyes. You've interacted with the world of light before. What we're interacting with when we see things is visible light, which is just a tiny portion of the electromagnetic spectrum. The electromagnetic spectrum at the full range of all possible wavelengths of light. All the wavelengths of light range from the most energetic, from gamma rays, to the least energetic radio waves. Pulsar jet emission, it turns out, is strongest, most easily identified in radio wavelengths. So this is light where if visible light, the wavelength of light, so like the distance between the peaks of the light waves, is something like 10 to the minus 6 meters. The wave, which is maybe like protozoan scale, according to this figure, the wavelength for radio waves is like 10 to the 3 meters, so like building-sized waves of light. These are not light that you can see with your eyes, but it is light that we can observe with the appropriate telescopes. It turns out it takes some of the biggest steerable things in the world to be able to observe radio waves. Radio waves do make it down to the Earth's surface, so we are able to make observations of radio waves on the Earth with telescopes on the Earth, which is good because since they are such long wavelength, it actually requires a very large dish to capture these waves. So I've put images on this slide of a few of the biggest radio telescopes that we have in operation. There's the Parkes Radio Telescope in Australia, the Green Bank Telescope, which is actually just in West Virginia. And that's a telescope that I enjoy visiting and enjoy taking students to whenever we get the chance. And then the Fast Radio Telescope in China is this truly ginormous 500-meter aperture telescope. Okay, so we have these telescopes that can observe radio waves, and we've got an interesting dense object, neutron stars, that, if they're pulsars, will be emitting these radio waves that we should be able to see in our data. But it takes a little bit, there's a lot of other things that emit radio waves. There's a lot of noise in our radio data that we have to be able to sift through to see if we actually have pulsars in there. So what happens is our radio telescopes collect the data. There are various algorithms that we use to try to put this data into some more useful formats. And in the end, the thing that would come to the scientist who's trying to find pulsars with radio telescope data would be a series of plots that looks like this. I'm not too interested in the details of all these plots, except in saying that there are diagnostic plots. There are trends we're looking for in these diagnostic plots that as a human you can look at and say, oh, this looks good, this doesn't look good. And these trends are things that are visible patterns in the images. So for example, in the plot that's marked time domain plot and subband plot, these two plots, we want to see vertical lines. So this data that I'm showing here is an example of actual pulsar data. This is what a pulsar would really look like. Right now, most of the work to go through all of this radio telescope data and identify pulsar candidates is done by scientists. And it takes a very long time to go through all of the radio telescope data to identify all of the potential pulsar candidates that live in that data. But this is exactly the type of problem that a computer could learn to help us with. And so that is one of the things that my research lab has worked on is writing computer programs that will help us identify pulsar candidates in radio telescope data. But before I show you that specific application and how it works, I'm going to need to tell you a little bit about machine learning. Most generally, the Oxford Dictionary defines artificial intelligence as the theory and development of computer systems able to perform tasks that normally require human intelligence. So that's a very broad, like sweeping term. AI is like a catch-all term that encompasses so many things. Machine learning is a slightly more specific version of AI. So machine learning is going to be the use and development of computer systems that are able to learn and adapt without following explicit instructions. Machine learning is the AI specific application that I use in my research, but even machine learning is pretty broad. In pretty broad strokes, if we were to compare what a traditional program might do to what a machine learning algorithm might do, if you think of writing a traditional computer program, traditional computer program, you would have a set of rules and some data that go into the program, and the program applies these rules to the data, and it spits out an answer of some kind. You could insert whatever specific problem you want into this formalism. A machine learning algorithm, on the other hand, flips things a little bit. So a machine learning algorithm, you don't need to know the rules. The machine's going to learn the rules. All you need is the data and the answers, and you have an algorithm that deduces what the rule is that connects the data to the answers. And then you're able to use what that machine has learned to get answers out of new data that's sent through the algorithm. Machine learning encompasses a lot of different branches. So there's unsupervised learning, reinforcement learning, and supervised learning. My work focuses on supervised learning. Those are the algorithms that we use in my research lab to tackle actually a number of different problems. Supervised learning, you can think of breaking down into two different categories. There's the problem of classification. Well, maybe I should say supervised learning generally is going to be a machine learning algorithm that gets a data set with answers defined by the user that it's able to deduce the rules through an algorithm that takes known answers and tries to iterate on itself to get itself as close as possible to those known answers. And then you can apply that algorithm to something new. We'll see. I'll go through that in a little more detail in a few slides. Generally, you can break this out into two categories. There's classification problems and regression problems. Classification problems, the output of an algorithm, a classification algorithm, is going to be putting something into a certain category. So you could have a binary classifier would put things into either true or false categories, or, thing A or thing B. But you could have multi-dimensional classifiers too, that maybe you can imagine writing an algorithm that takes a piece of fruit and categorizes it as an apple, an orange, a banana, or a pear. You could make however many classifications as you want, but in the end, you have a probability that something lives in a given class. Regressions, on the other hand, predict numbers, like continuous numbers. So a regression algorithm might predict gas prices or the weather, or something that's on a continuous scale and not a discrete classification problem. Neural networks are, I'm going to focus on neural networks in this talk because neural networks are the machine learning algorithms that my lab uses most commonly in my research. Neural networks are one type of supervised classifier. There are other supervised classifiers as well. So we're just kind of narrowing in further and further. You can have neural networks that are classifiers or regressors, either way. A neural network is built from neurons. So these are modeled after the brain, where one piece of the network is known as a neuron. And most generally, broad strokes like black box, the neuron takes some input. Here I've defined 2 inputs, but it could be any number of inputs, does something in that box, which I am going to reveal in a moment, and then predicts an output. If it's a classifier, that'll be some number between 0 and 1 typically, or set of numbers between 0 and 1. Or if it's a regressor, it'll be a generic number or whatever it might be. The next few slides, I want to reveal this black box a little bit for neural networks, just because I always found it frustrating to not know what was going on inside the box. I want to understand the box. So I do have a bit of math on the next few slides. If this is something that interests you, please follow along. If you want to tune out for 3 slides, you can join me again in 3 slides. So to open that box a little bit, what's happening inside a given neuron is that the inputs are getting multiplied by something called weights, added together with an extra piece called a bias, and then sent through something known as an activation function. And then the input of that neuron takes in all the inputs, does these manipulations where it multiplies by weights, adds everything together, adds a bias to it. I'll explain the activation function in the next slide. And then the output of that algorithm, the output of that operation is some number y that is the result. The activation function is the thing that's going to map the range of your output to something that you desire. So this function, if, for example, you want to have a classifier where the output is a number between 0 and 1 that you can roughly interpret as a probability that something lives in a certain class, like I send in an apple and I want you to tell me the probability between 0 and 1 that this thing is an orange. I would hope I get a 0 out, but we'll see how good my algorithm does. I need to tell this mathematics to map the input, however I've quantified the characteristics of my orange. I need to tell it how to map those numerically, to what range to map those to. So if I want to map it between 0 and 1, a very common activation function to use is something called the sigmoid activation function, that you can think of your input as the x-axis here, and your output is the y-axis. So for a given x value, you would map to a specific y value given this function. A neural network in general is not just composed of one neuron, but it's composed of many, many neurons, and potentially many layers of neurons. So each of these circles is meant to represent a neuron, and each column of circles is meant to represent a layer, where the first layer is going to take the actual inputs, the data inputs that you're giving the algorithm. And then any layer after that is going to take the outputs of the layer before. And each of these neurons is doing that set of mathematical operations. And then you will have, if you have something that's making one prediction as an output, you would have one output neuron that would map all of the stuff that's happening in the middle to one number coming out. If you have multiple outputs, multiple things that are being predicted, you just have multiple neurons coming out of this picture. Neural networks are, like I said, supervised classifiers, which means that they require training on data sets that people have made. Making a training data set is often one of the hardest parts of using neural networks. The process of training, you have a set of data where you know the inputs, you know what the answer is for a given set of inputs. So if it's a classifier, you have inputs and you know exactly which class each of these inputs map to. And so you start off with random initializations for the weights and the biases of every single neuron in your network. You send in a set of inputs, you send it through the network, and it spits out a prediction Y, which is likely nowhere close to the actual answer for what this classification should be. Then what you do is you tell the network what the actual value of Y was, because this is your training data, you know the answer. You give it the prediction from the network, and it uses a process known as backpropagation to update the weights and the biases of the network, and that feeds back into the network, and you do it again. You send in a new set of inputs, makes a new prediction based on those updated weights and biases. You compare that to the answer, and you keep going for as many iterations as you decide is necessary to reach some accuracy that you decide is necessary. There's actually a lot of different types of neural networks. There's artificial neural networks. These are probably the simplest. This is what I basically just laid out on the previous few slides. These pass information along from one layer to the next in a forward direction. There's convolutional neural networks. These are really popular for image classification because they use a set of filters on each of the layers to learn specific patterns in an image. And there's recurrent neural networks. These are pretty popular for natural language processing. They're really good at dealing with sequences, and they also can actually deal with variable lengths of inputs and outputs. Okay, so that's my introduction to machine learning, very specifically to neural networks, which is going to be the applications that we use. So back to the problem we're trying to solve. We have these really dense things called pulsars that are emitting radio waves. We can capture those radio waves with our radio telescopes, but we have this really tedious problem of trying to figure out which of the things in our data are pulsars and which of the things in our data are noise or not pulsars. We're going to be able to use machine learning, neural networks, as well as other classifiers to help solve this problem. The way we do it is we give each individual plot becomes the input to a specific classifier, like an ANN, an artificial neural network, for example. So if I'm taking one of the plots from this previous page, this was the plot on the top left, and it's really a discrete set of data points. So all the green dots on here are showing you really my data is sampled at this point, and this point, and this point, and this point. It's not actually, a continuous function or something like this. So each of these green dots is actually an input to the neural network. And what the pattern that the neural network has to learn is that for pulsars, you get peaks in your data that rise above the background noisiness. And these peaks tend to be kind of narrow. And so you feed lots of known pulsars to the neural network with it the answer that it's a pulsar. And you also feed it lots of noise with the answer that it's noise, and it learns to do this classification. This is, as I just said, a classifier problem. So the prediction that comes out is a number between 0 and 1 that corresponds to the probability of this thing being a pulsar or not a pulsar. We do this for each of our plots. In general, each of our plots gets sent through typically 2 different machine learning algorithms. Each of those algorithms makes a prediction about whether the thing that's coming out is a pulsar or not. And then we send that to a different machine learning algorithm, we're calling our combiner on this, whose input is the predictions from all the things above. And then it makes one final prediction about, given all the information from these 4 plots, is this piece of data a pulsar or not a pulsar? And then the applications of this are that we as users can then run our data through this machine learning algorithm, and we can then filter the results and say, I want to see the things you think are most likely a pulsar. And then I can go in as the scientist and not have to weed through as much noise and more efficiently identify new pulsars and do all the cool science that comes from discovering one of these new, dense, rapidly rotating, highly energetic objects. So in summary, machine learning helps us find new pulsar candidates in generally noisy telescope data, which is a really interesting problem to solve, but is actually probably not even the main focus of my research program. You might ask, maybe you're sitting there wondering, wow, these neutrons sound super cool. Is there any other way I can learn about them? Or you might be thinking, you told me about something denser than a neutron star. You told me about a black hole. How can I learn about things like black holes? Well, we'll start with the first question. Turns out the neutron stars are made of this really dense matter that I already said is, 1 teaspoon is 10 million tons. This is not densities we can make on Earth. And so this is not a type of matter that we can study on Earth. The only way we can study this state of matter is by trying to figure out what's going on inside of the neutron star. Or the way we would describe this is we want to learn about the relationship between how the matter behaves at different pressures and densities, which is what we call the equation of state of matter. You may have seen this in a high school chemistry class. You may have heard of the ideal gas law. This is a relationship for a type of matter known as an ideal gas between pressure and temperature. Neutron star matter is not an ideal gas, so that would not be the correct relationship for neutron star matter. In fact, the equation of state for neutron star matter is unknown at the moment. We have some restrictions on what it should be, but it is really one of the current scientific frontiers where we're really trying to understand how this matter behaves at these extreme densities. Roughly speaking, light, like the radio waves coming from our pulsar, can tell us things about what's going on the surface of a neutron star. But it's not super great at telling us about what's going on the inside of the neutron star. For that, we're going to need a different type of messenger. Additionally, the other question I posed a few slides ago was, what about these other dense objects? The densest thing you can make is called a black hole. Black holes are going to be areas of space that are so dense that you would actually have to be capable of traveling faster than the speed of light to escape the surface of that object. So if you think on Earth, we can launch a satellite or a space shuttle or whatever it might be off the surface of the Earth, and it can leave Earth's gravity and go travel to other places. And we don't have to launch that thing faster than the speed of light. That's because the Earth's gravity is not so strong that it requires that immense speed. Black holes are objects that would require faster than the speed of light motion to leave the surface. Since nothing can actually travel faster than the speed of light, this means nothing actually can escape the black hole, including light itself. And this is why these things are called black holes, because they appear on the night sky as just black spheres. There's no light emission or other emission coming from them. The way to understand black holes is going to come through Einstein's theory of gravity, which is known as general relativity. So Einstein's formation of what gravity is that it is a geometric result of how space-time is shaped, I guess, most generally. So if you think about space-time as like a fabric, maybe a bouncy sheet is a nice way to think about it. And if you put a mass on that sheet, it's going to cause that sheet to cave in. And now imagine rolling a marble across that sheet. That marble is going to fall into the dip that the mass caused. This is gravity. That marble is traveling the path that it knows to take on this curved sheet, and that path ends up taking it towards the other mass. What is gravity but two masses getting attracted to each other? And in Einstein's theory of general relativity, that comes out of these objects just traveling along paths in a space-time that is curved. So John Wheeler summarized this as space-time, generally the geometry and the curviness of the space-time tells matter how to move, and matter tells space-time how to curve. The mass of your matter is going to dictate how much curviness your space-time gets. So the sun might make like a little dip in space-time, which means, you know, if I'm out there, I'm going to be attracted towards the sun. I'm going to take a path that might pull me towards the sun, but it's not impossible for me to go past it or to stay away from it and orbit kind of far away. A neutron star is going to have a much bigger dip, a much larger curvature in space-time, which is going to lead to more extreme orbits, more extreme gravitational effects. And a black hole is the ultimate extreme of this, where you have an infinite curvature in space-time caused by what we call a singularity, basically all the mass collected at a single point. The other great thing about Einstein's gravity is that it predicts an elusive messenger known as gravitational waves. So as you spin objects around or wiggle objects around in space-time, it causes ripples in the space-time curvature. This is a lot like if you were to throw something into a pond and you get ripples of the surface of the pond that kind of propagate out towards the edge of the pond. The masses, as they accelerate through space-time, are going to cause ripples in the space-time. And since gravity is space-time curvature, and we're wiggling masses around, changing that curvature, the gravitational waves are going to communicate information about how gravity is changing. So that's a fairly abstract thing. What does this mean? How does this actually affect me? Well, it turns out these gravitational waves, these little ripples in space-time, do have a measurable effect on matter. So if the gravitational wave was passing through your computer screen and you had a little ring of particles that you were testing to see what it did, those particles would squish and squash like this, essentially. And so the distance between particles on this ring is getting smaller and larger as the wave passes through. So if we want to be able to measure gravitational waves, which it turns out is going to be a useful thing to do when we try to study dense compact objects, we are going to need to be able to measure really precisely distances between 2 points in space. A very useful tool for doing that is something known as an interferometer. So an interferometer is a laser with a mirror. The laser, or beam splitter, I'm sorry. So the laser hits the beam splitter, half the light ends up going straight through the beam splitter, half is reflected off, and then it bounces off some mirrors at the end, bounces back towards the beam splitter, recombines, and hits a detector. Depending on the way the light recombines, the light is either going to recombine constructively, so this will happen if light, we already saw light as a wave on that electromagnetic slide earlier where we were looking at different wavelengths of light. When you have waves and you add them together, if you make a peak of one wave meet a valley of the other, it cancels out and you would get no light. But if the distance between the beam splitter and one of these mirrors changes, maybe due to a gravitational wave, that's going to change the way that light recombines. And you're going to be able to get a signal out at your detector where you would normally expect nothing. And so if we can measure how much light is hitting our detector, and we see a change from nothing, that tells us that something has changed the distance between our beam splitter and our mirror. Turns out the thing doing that could be gravitational waves, or maybe it's other things. But this is certainly an effect that a gravitational wave would have on the detector. And so as long as we can build something that can measure the expected level of changes in length, we would be able to measure gravitational waves with a device like this. Okay, so what makes gravitational waves? Well, actually anything that accelerates through space-time makes gravitational waves. So like I can shake my hands around and make gravitational waves. Turns out those are so small that no one has any hope of ever detecting them. The most fruitful astrophysical source for gravitational waves actually ends up being the merger of very compact objects, things like neutron stars and black holes. And by the merger of these objects, I mean that if you have, say, 2 neutron stars orbiting around each other, it turns out as they orbit, they're going to lose some energy from gravitational waves. And as they lose energy, that's going to cause them to fall towards each other. And as they fall towards each other, they're going to speed up, which is going to make more gravitational wave emission, which is going to cause them to lose more energy, which is going to cause them to fall. And the cycle continues until the objects end up right on top of each other and merge into a new object, typically a black hole. What that looks like in terms of your data is, in terms of the gravitational waves that would be produced, is if this is a plot showing time across the horizontal axis, and vertically, you can think of this as the strength of the gravitational wave. So you can think of this as the squishing and squashing of that ring of test particles a few minutes ago. So as the wave comes through, they're going to get closer and further, and the wave's amplitude is going to increase, and the frequency, the rate at which things are getting squished and squashed, is going to increase with time until these objects merge. When these objects merge, they are going to settle down into a new object that's nice and spherically symmetric, and it turns out does not cause any gravitational waves. So how strong are these gravitational waves? Turns out not super strong. So the most dramatic astrophysical event you might be able to think of, like two black holes smashing into each other, is going to cause a change in distance over a few miles that is less than the width of a proton. So we started there looking at an electron orbiting a nucleus, and now we're zooming all the way into the proton. And the type of wiggle we can expect in space-time from these gravitational waves is like this, like 10 to the minus 18 meters across a distance of like several miles. So pretty small and pretty hard to find. In fact, Einstein predicted the existence of gravitational waves back in 1915, and it took over 100 years, almost exactly 100 years, to make the first discovery of them. He didn't think they would be something that would be detectable because these predicted changes in space-time distances were so small. The thing that ended up making this possible are observatories known as LIGO, the Laser Interferometer Gravitational Wave Observatory, and the partner observatory Virgo in Italy. The LIGO observatories, there's two of them in the US. One is in Washington State and one is in Louisiana. And then there is another detector in Virgo. These are basically huge kilometer-sized versions of that graphic I showed several slides ago, the interferometer with the laser beam and the mirrors. So if you're looking at these aerial views, the lasers are housed in the buildings, kind of in the middle of this, this right angle here. And then those arms are the arms that the laser travels down, and then the mirrors sitting way down at the end, several miles down the road from the laser. There's a network of these observatories around the world. So there's the two in the US, Virgo in Italy. There's also a much smaller scale detector in Germany, GEO 600. There's a detector in Japan known as CAGRA, which is just coming online and starting to take some of its first data alongside LIGO and Virgo. And then there's a detector planned to be built in LIGO India. As the US-based detectors, LIGO is the specific detector that my research group is a part of. So the LIGO Scientific Collaboration is the group of nearly 1,000 scientists from hundreds of different institutions who contribute to the science of these detectors and of this field. And you'll see if you zoom in, Kenyon's part of this group. The very first detection of gravitational waves happened in 2015, on September 14th, 2015. We had actually just finished upgrading the two LIGO detectors. We turned them on, and nearly immediately, we saw just this beautiful merger of black holes. It was like exactly like what we would have thought it would look like. It was loud and it was clear. What you're seeing in this picture, I hope this picture looks familiar from a few slides ago, which was the theoretical prediction for what this black hole merger would look like. And when you see it in the data, the theory matched the data beautifully. And this ended up being a very significant detection, which marked the first direct detection of gravitational waves, as well as the first observation ever of a binary black hole system. So that would be two black holes orbiting each other. This is a numerical relativity simulation of what that merger might have looked like. So what you're seeing here are two black holes orbiting each other. They will speed up in their orbits as they fall closer towards each other. They're emitting gravitational waves, which is causing wobbles in space-time. And you can kind of see that in the surrounding stars because the light coming from these background stars is going to get affected by gravity. And then in the end, these objects merge and become one final black hole. This discovery won the Nobel Prize in Physics in 2017 and was one of the, in my opinion, the most exciting discovery of the century, but definitely a very well-received advancement in the field of gravity. To date, that was 2015. To date, we have published on close to 100 detections of either two black holes, a neutron star and a black hole, or two neutron stars orbiting each other and merging. We actually have well over 100 things at this point because we are in the middle of another data taking run. But the most recent things, while they are publicly available as preliminary data, we have not published our final results on them. So nearly 100 published detections so far. All right, so that was a nice background on a new type of messenger that you could use to learn about something like neutron stars. So back to my main storyline here. Can gravitational waves teach us something about neutron star interiors, this thing that light from our radio telescopes, for example, can't? To see how you might be able to learn something about neutron stars from something like gravitational waves, we need to understand a little bit about what's going to happen to neutron stars as they orbit and merge. So neutron stars, as they orbit each other, are going to actually deform as they get close to each other because the side of the one neutron star that's closest to the other one feels the gravity of that other neutron star more strongly than the backside does. This is actually the exact same physical effect that causes the ocean tides on Earth. That causes this deformation in the shape of the neutron star. So the neutron star kind of gets squished as it gets close to its partner. Both of the neutron stars squish as they get close to each other. And it turns out that the amount that the neutron star squishes is actually related to the equation of state of the neutron star matter, as well as the size of the neutron star. Well, really, the equation of state will tell you the size, which will then tell you how much it's going to squish. And it turns out that gravitational waves encode information about how deformed these neutron stars get as they orbit each other. The deformability is described by two parameters, lambda1 and lambda2. They'll come up in a few slides, so I'm putting them here. But these are generically the parameters that tell you have star 1 and star 2, how much did they deform as they were orbiting each other. Different equation of states. Equation of states you can kind of classify into two categories. There's the hard equation of states and the soft equation of states. The hard equation of state is going to lead to neutron stars that are bigger, which is then going to lead to a larger deformation as the neutron stars get closer to each other. A soft equation of state is actually going to lead to a neutron star that's physically smaller. The radius of the star will be smaller, which actually is going to lead to a smaller deformation. So we'll be able to categorize by looking at the gravitational waves coming from the merging neutron stars, how much they've deformed, which will help tell us something about the equation of state of the neutron star. Okay, so there's lots of possibilities for what the equation of state might be. So this is a plot showing, this came up on the earlier slide. This would be an example if we could classify how which of these lines tells us about what the pressure and density of neutron star matter, how it actually behaves. So each of these lines represents a different possible equation of state. We don't know what it is, so we don't know which of these lines is right. But we know there's some line through this pressure density space that would correctly classify the equation of state. Since we don't know what that line is, we can just generically come up with a way to parameterize how those lines move through the space. So it might be a line that looks like this, or like this, or like this, or like this. And in general, we can come up with a set of parameters called here M1, M2, and a set of gammas that will give you the rule for how to draw that line through space. Unfortunately, gravitational waves don't tell us about equation of state parameters directly. They tell us about how squishy the star was, how much did it deform through parameters like the masses and the lambdas, these deformations. And what we actually want to understand the fundamental physics is the parameters that tell us how to draw this equation of state line through mass and through pressure and density space. And this is another place where we are using machine learning to help us do this mapping. So we're actually this is a somewhat new project that was initiated by Professor Les Wade at Kenyon to teach computers how to learn the mapping from the tidal parameters, the thing that the gravitational wave tells us, to the equation of state parameters. So if we go back to our picture of what a machine learning algorithm looks like, in this case, we're using a neural network, an artificial neural network, but it's a regressor this time rather than a classifier. It's going to predict a number rather than a probability of being in a class. And in fact, it's actually going to predict 6 numbers. The input of this is going to be, for a given set of stars, it'll be the masses of the stars and their tidal deformabilities, these lambda parameters, so how squishy they got. We're going to teach, we're in the process of teaching an artificial neural network how to take those inputs and predict the masses and the parameters that tell us how to draw the equation of state. This project is looking hopeful. We don't have results on it yet, but it's looking hopeful. Isa Braun, who's a current sophomore at Kenyon, has been working on this. And this will really help improve the efficiency of doing this mapping from gravitational wave detections to these fundamental physics parameters about the equation of state. Okay, in my very last minute or two here, I want to tell you, like really literally in 2 slides, about one other project. It is actually the longest standing machine learning project we've been doing in our research in Kenyon's gravity group. Anyway, I'll tell you about it, but it is briefer. I just didn't have enough time to tell you all the things. So this project is related to using machine learning to help predict the presence of noise in LIGO data. So this schematic is meant to roughly show you what that means. So we have astrophysical signals like, these merging neutron stars or emerging black holes that affect our detectors on Earth. However, I told you that the disturbances caused by these astrophysical signals are things like disturbances less than the width of a proton across miles-long distances. It turns out these detectors are on the Earth, and a lot of things shake your mirrors by much more than the width of a proton across these miles-long distances. All of those things that shake our detector that are not of astrophysical origin are things we call noise. And the noise pollutes our data and can affect our ability to pull out astrophysical signals. But if we can identify whether noise is present with some confidence that, this point in time had a loud noise event, we can use that information to improve our statistics and our confidence in any astrophysical signals we detect. However, identifying noise is a little tricky. What we use, though, is what's known as auxiliary detectors. So these are going to be different things like seismometers, microphones, thermometers that are on the LIGO Virgo detectors. Well, this project has specifically been applied to LIGO. So on the LIGO detectors, monitoring the environment around the LIGO detectors, as well as the different feedback loops and lasers involved in the detector itself. And we're going to look at these noisy things that are going to affect our main detector are also going to affect our auxiliary detectors. And so the idea is to teach a machine learning algorithm to identify noise events by looking at the auxiliary detector data and use that to predict whether or not there is a loud noise event, or what we call a glitch, in the main detector at a given point in time. So here's a picture of what the current state of that algorithm looks like. It's evolved a lot over the years, and I've listed the many students who have worked on this project, starting in 2018 all the way to the present. It's still something that's going on. We have evolved this algorithm over the years. We've tried lots of different things. It turns out this is a pretty hard classification problem to do because there's a huge amount of data going in with lots of different possible sources of noise. So the thing we've been exploring most recently is if you take your data and you break it out by auxiliary system and try to teach individual machine learning algorithms different things about different features of the noise, and then combine all those outputs together, it turns out you can do a much more robust job at predicting the noise. And we're taking this one step further, something that students will be working on this summer, into instead of looking at different auxiliary subsystems, what if we look at different classes of things causing the noise? So, things like scattered light, noise caused by light scattering in our detector, noise caused by an earthquake, noise caused by something else, and teach individual, whether it's neural networks or different classifiers, about different types of noise to become experts in given types of noise, and then you combine all of those predictions together to give you one final prediction. So I'll just conclude by saying machine learning is becoming increasingly sophisticated. So what I've talked about here is what we would call pretty old machine learning at this point. Neural networks is kind of old news. But even these rudimentary neural networks are incredibly powerful and incredibly useful in solving a lot of our current scientific, in meeting a lot of our current scientific needs in data processing and analysis. So currently in Kenyon's gravitational wave group, what we are using neural networks to do is to do things like identify new pulsars and radio telescope data, improve the efficiency in how we measure the neutron star equation of state, predict the presence of noise in the LIGO detectors. And I didn't even get to talk about this one, but a brand new project that will be starting in the coming months, which will be learning how to, using machine learning to actually help us calibrate the LIGO detectors themselves. So that is it for my slides, but I think we've left some time for questions. So I am actually going to stop sharing so I can see the chat, but I'm happy to take any questions folks might have. Or if not, I don't have to. Oh, I do see. So a lot of the question in the chat was, what software are we using for machine learning? It varies a little bit. We've used a lot of the TensorFlow machine learning library, which is Google's machine learning tools. We've also used scikit-learn, and PyTorch is one that I've started to think about but haven't done much with yet. There's lots of new exciting things out there. This sounds like a great opportunity for students. It seems like the research students are doing what would be more at graduate level institutions. Yeah, so actually, definitely our students who continue working with us for a few years or do one or more summers of research with us, when they come out of that, I would classify them as graduate student level workers. In particular, any of our students who do projects, senior honors projects with us, where they're, in addition to doing summer work, they're spending their whole senior year focusing on a research project and producing a thesis out of that project. In fact, I actually have to, in my MOU with the LIGO Scientific Collaboration, I have to report on everything my students do, and I have to classify them in categories. And there's a category that basically puts them in grad student level productivity. And every year they're always surprised at how many graduate student level students we actually have working with us. Yeah. Okay, well, if there's no other questions from folks, going once, going twice.
Hey, Maddie.
Oh.
Hey. I was wondering on your slide where you're predicting equation of state with ESA, where are you getting your classifications from? Because it would seem to me that that kind of, the true parameters you're looking for are kind of hard to obtain.
So we're just learning the mapping. That's a great question. So yeah, we don't actually have the answer for what the equation of state is, but we do know how to map from lambdas to equation of state parameters.
Okay.
So we are basically using, it's called a prior run. We're basically using the data that tells us the mapping from, if I feed all of these parameters in, this is the equation of state that would come out for the algorithm to learn the general way to get from one space to another. So then if we had an actual detection, well, we've had one so far. If we have another actual detection of neutron stars where we can extract tidal information from them. Then we could feed that into the algorithm, and it would only map to one line, which we don't know what that line will be yet, but it would have learned the general mapping of, given these inputs, this is how I get to the output. But the thing we're training it on is like the biggest possible space for allowed mapping. So, you know, it learns how to go from anywhere in the possible realm of equation of state parameters.
Okay, so this is all still based off of simulation in some sense.
Yeah, so the data that we're using to train is all just using, there is physics relationships that tell you how to go from the lambdas
Yeah,
to the
this is
equations.
relativity.
Yeah, and that's specifically using the TOV equations to get from one of those.
Okay. Okay, thanks, Maddie.
Yeah. Well, thank you all for coming. And thank you, Paul was one of the people who did some of the great work on the project I mentioned at the end. So nice to see you.